Yeah, so this is talk about MariaDB Vector search. Yes, let's see this slide. So I'll start from gentle introduction of what is this talk about, and I'll explain in different words I'll be using. So what is vector search? Vector search is a technology that lies behind some of the user-facing features such like semantic sets, text search, image search, music search. Could also be video search. It could be hybrid search where you, for example, use text to find images or use, I don't know, music to find text, something like that. And behind, very popular nowadays, RAG, which is Retrieval Augmented Generation, which is used in various chatbots that, well, talk with you about whatever you want to know. Vector search is the technology that is beyond Golubchyk. And how does this work? Conceptually, it's very easy. You have, as I said, images or music or video or text, whatever. You convert everything into vectors, install those vectors into database. When the user wants to find something, you convert user request, which is again video, text, or music, humming into the microphone, whatever. You also convert it into vector, and then you use vector search. So easy. The trick is, of course, that vectors are created in a way that similar information, similar text, similar music, similar images have similar vectors, and if dissimilar images or information have very different vectors. So that's the whole trick beyond this, and how to do that is completely beyond the scope of this talk, because this is not done by the database. This is done outside of the database. So again, the vector that I am using and will be using through the whole talk. What is a vector? A vector is basically just a list of floating point numbers, something like that. And typically it has like between few tens to few hundreds up to a couple of thousands of numbers inside one vector. And all vectors usually have the same length. And the search for vectors that I said here, vector search, yeah, that's too slow. It searches for the closest or nearest vector, because nearest vectors mean information is close to each other. And the search, it's very important. The search for the nearest vector is always approximate. I mean, to my knowledge, there are no practical, fast, exact algorithms to search for nearest vector to nearest exact vectors of that length. So all the practical approaches are approximate. And this is not really what normal SQL is about, but in this case, yes, vector search is approximate. And the last new word I'll be using in this talk, there will be MHNSW used throughout the talk. What is this? So MHNSW, it's hierarchical navigable small world, is the name of the vector search algorithm, which is basically, yeah, it's industry standard de facto vector search algorithm for approximate nearest neighbor. It's like, you know, the best over the various range of practical applications. It's not always the best. I mean, it's worse than others in some corner cases, or for example, if you use completely random data, but practical data are not really random, and then it's basically it's optimal. It's fast enough and it provides good enough results. Other leads are either they are much faster, but results are, let's say, much more approximate, basically correct, or they could be very exact but unusually slow. And this is one like optimal one. And pretty much every vector search database, practical vector database uses implements this and maybe a few others, but this one is pretty much everybody is doing that. And MariaDB uses a modified version of MHNSW, that's why we call it MHNSW. So let's start from the example. So there's a vector data type and the vector index. So all you need to do is basically create a column with the type vector. This is the number of the dimensions, a number of those floating point numbers inside one vector. And 1536 you might see a lot of times, because if you use OpenAI to generate vectors, OpenAI returns vectors of 1536 dimensions. Then you create a vector index over the vector column. That's how a table looks like. You can optionally specify various parameters. Well, two. You can specify the distance and the m, and I'll talk about that later. Then this is an example of Python code of how to generate vectors embedded using OpenAI. It's just using OpenAI Python module and connect it, and we take the text and retrieve the vector. And to insert this embedding into the database, we just get the embedding and insert it using a vector from text function, which takes this vector with the square brackets and numbers and insert it, and this is just a number, and insert it into embeddings table that I've just shown. This test takes the vector, converts it into the string, and this function converts the string from the vector from the string into the binary vector, and inserts it into the database. This totally works, but it's possible to avoid those two vector to string, string to vector conversion and make it faster. This is by just inserting the vectors in binary. So this one takes the vector directly and converts it using Python array module just to string of bytes, and you can insert those bytes directly in the database, which is of course clearly more efficient, as you avoid the centralized state of the server and you don't convert it float bytes to string and then string to bytes again. Did you want to say something?
That has to happen on a little engine.
2
bytes is engine dependent.
Maybe. Maybe you can specify this in Python. I didn't check that.
Yeah,
well, that works on my laptop. And on the benchmarking machine, yes. Searching works. As for searching, the execute and Python is the same, but the logic here is we want to find the nearest vectors. So we just sort by distance, and we take like 5 first matches. This is normal SQL for finding 5 nearest something, and this works with vectors exactly the same way it would work with anything you might think of. But so this is how it works with raw SQL and Python. But practically, you will not be doing that. I would expect that most of the users will not be doing Python directly accessing the database. They will be using some AI framework like LlamaIndex or LangChain or SpringAI. And this is how. And from LangChain, you just import MariaDB Vector from the vector stores and create a vector store. And everything else in Llama, you do it in LlamaIndex exactly as it would be done with any other vector store, MariaDB Vector, PG Vector, or anything completely in memory. So after that, LlamaIndex hides all the details from you. So this is the only thing which would be different if you use MariaDB in LlamaIndex. And here you see the same number that I've said you'll be seeing more. And this is, LangChain is, pretty much the same. You create MariaDB store. You can also specify the distance strategy. Otherwise, it's pretty much the same. And beyond this statement, there's not much specific to MariaDB if you use an AI framework. So the important part is how you tune MariaDB vector search to perform well and deliver the quality that you need. The thing is, tuning the vector search is hard. In modified MariaDB algorithm, there are lots of tuning parameters, more than 10, and they interact with each other in complex and unobvious ways. It's impossible to describe what they do in easy words. We would need to understand exactly how the algorithm works to understand what every parameter changes. And this is not what we want users to dive into. Well, some people might want to know that, but normally we don't want users to, well, and get complete understanding of how vector search works before they'll be able to tune it. So our approach was we hide these parameters, we select best values, we configure them to be auto-tuned as needed, and we only allow users to tune the absolutely smallest number of parameters which is required, which is necessary. We cannot remove any of those parameters that are still left tuning. And there are 4 of them. Those are parameters that database cannot automatically decide on. The first one, these are, I'll just show what they are and their values, and there will be explain them in details on a later slide. So, MHNSW, so max cache size. So what's important to understand that this algorithm, HNSW, hierarchical navigable snowboard, it's in-memory algorithm. It basically works, well, it performs only if the whole data, all the vectors are in memory. In MariaDB, it will read the data from disk as needed, but until all the data are in memory, the performance will be not very good. It will be slow. So you would want to have this cache size as large as possible. MariaDB will not use it, will not use the whole memory. The cache will grow as needed, and the largest value it will take will be basically the size of your index. So if you have only 2 gigabytes of the vector index, you can safely set max cache size to 10 gigabytes. You will never use those 10 gigabytes. But you want to set it as large as possible, as large as you can afford, to make sure you get as much data as possible into memory, because that's the only way you can get any, well, usable performance. The distance parameter, it is something you specify per table. And if you do not specify it per table, then this variable default distance will be, that's where the variable comes from. It takes two ways. Could be either Euclidean or cosine. The thing is, so what I said in the beginning, when you generate vectors, the most important part is, well, that's the whole thing that makes the vector search work. If the data are similar, like if this image is similar to this song, whatever it means, then those vectors should be near each other, and if the data are different, vectors should not be near each other. And vectors are near each other using a specific distance function. So depending on how your vectors were generated, depending on what you use to generate vectors, and then they would be either your code for generating vectors, generates vectors which are close to each other in Euclidean space, or close to each other using cosine distance. So basically you said this is not really a tuning parameter. This is something that describes your method of generating vectors. And for OpenAI, for example, you can use either, because OpenAI returns vector of length 1, and those two distances, they basically return the same value. It doesn't really matter. But for other ways of generating vectors, it's important to use the same distance that those vectors were generated for. And now there are two really tuning parameters. One is called EF search, and one is called M. The M is again specified per table. If you don't specify per table, then default M variable will be used. And they allow you to tune the vector search in 2 different dimensions. You have two degrees of freedom. The search can be, that's always the trade-off. So either you have the search fast, but the results are not very precise, because again the search is approximate, and the more proximate it is, the less meaningful results it will return. So either it will be like very fast but not very precise, or it will be very slow and very good, very relevant results, or it will be something in between. If you improve the quality of the search, which is the number called recall, the higher recall closer to 1, then the speed will go down. If you improve the speed, then recall will be decreased. So this is how you can tune it. But also, to get a good recall, you need to do a certain amount of work. And then you can decide when you want to do this work. Either you can have very fast inserts, and then you need to have slow selects to have good recall. Or you can have a very good, very slower inserts, meaning, excuse me, you can have a slower inserts, meaning most of the work to achieve a good recall would be done during inserts, then selects will be faster for still the same recall. So this means you can two dimensions to choose whether you want faster search, faster operations, burst recall, or slower operations, better recall, and then after you decided, well, what kind of recall you want, you still want to tune whether you want to have slower inserts, faster selects, or faster inserts, slower selects. That's why two degrees of freedom, you have to have two variables to tune that. Those variables are EF search and M. EF search only affects the search, improves the search, and M affects both. So if you increase M, both inserts and search become slower. If you increase EF search, only the search becomes slower. And I'll show you how it looks. So this is, yes. This is one of the data sets benchmarked for different values of, on MariaDB, for different values of M, EF search. So you can see, so on the horizontal axis, this is recall, it goes up to 1 meaning exact, and this is UPS queries per second. So two things you can see that it is indeed either when recall increases, search number of queries per second decreases, so the search becomes slower, and also if you increase M, you actually get better UPS, you get less drop in speed and better recall than if you would increase EF search. So normally it makes sense to increase M and keep EF search as small as possible.
So why wouldn't you make it 100?
Yes, I'll get to it on the next slide. And this is the build time, the time to insert all these those 3 million rows in the index. And as you see, as M increases, build time grows. First it grows slow, but then inserts become very slow. This is the recall one. So normally a tuning strategy is you decide how much insert performance you want. So for example, here you decide that you do not want to go beyond M equals 6. And then you decide that okay, you are here, and then you see how much of speed, search speed you can change to get a little bit more recall. This is a very big jump in recall. So what kind of recall you want? Practically, I've read in papers that about 95% is practically usable recall. Before that, you get too much unrelated data, and about 95% people don't see the improvement anymore with RAC at least. Well, at least that's what I read. Maybe some practitioners tell you. I've seen people on the mailing list, maybe 98% people will be better. So anyway, something around this line that should be practically useful recall. So this is all completely unusable, and I just show it to demonstrate the behavior of the variables. Yeah. So and now let's see how MariaDB compares with other vector databases in performance. I was using N benchmarks that Mark Callaghan was using also in his blog posts. This is, and I've compared MariaDB with all the vector databases that N benchmark has to offer, at least in those versions of N benchmark that I performed. So this MariaDB is compared with PG Vector, with Quadrant, with Redis, and with VV8. Quadrant and VV8 are dedicated vector databases. Redis and PG Vector are clear. So this is the same chart I've just had on the few slides before. This is build time versus recall. And those shows the best value you can get with any M and F. So actual lines go like this, but So this is the best performance, best recall, best QPS you can get for any given point. And this chart, they show a very small data set, only 60,000 rows of almost 800 dimensions using Euclidean distance. And here you can see that MariaDB and Redis Search do basically all the best performance, and everything else is 3-4 times slower. This is the Vector. And on the build time, MariaDB has the lowest build time. So this is a very small data set. Everybody is doing very good. You can recall is like perfect 96%, 97%. Let's get something more complex. This is a larger data set of 1 million rows of 906 dimensions. Again, using Euclidean distance. The picture didn't, in fact, change much. MariaDB still has the best recall, best build time up to 98%, and then Quadrant becomes better. On the other hand, Quadrant has a worst search performance of all, at least until 98%. So if I could get MariaDB down here if I would want to decrease our search performance as well. And again, MariaDB and Redis Search are like the fastest, and the other three are 3-4 times slower. And the last one shows something that I call like a difficult data set. Only 256 dimensions and about 300,000 vectors. This is New York Times data set. But it's difficult in a sense that so Redis indeed has a better performance here, but only at lower recalls, and it doesn't even reach 95% at all. So it's basically unusable. For this data set, you cannot use Redis. It's below 90%. And MariaDB is completely faster than anything else.
And then what does it mean what it can't reach recall? What does it mean?
It means that I run n benchmarks on using all those what n benchmark calls algorithms, and then I run plot script because and I got this picture.
So it's like you say, hey, I want a recall of 95% and the query.
No, I'm not saying it doesn't. You don't specify recall in your n benchmarks. You run it and you specify various set of parameters. Like you want to try values this and this values of m, this and this value of EF search, this and this value of EF construction. It tries all the possible combinations. It puts all the dots on the
Oh, I see.
And then it draws the best line you can get.
I see. So while you want, let's say, 95% recall, you kind of have to guess parameters.
With all those parameters that n benchmark has in configuration files, Redis Search didn't reach 90%. And this also actually answers a question of topic you mentioned in your talk, that if you tune this or you tune that, Postgres would perform better. I did not tune Postgres at all whatsoever because I'm not expert in Postgres tuning, I'm not expert in Quadrant tuning or Redis Search or VA tuning. I can tune MariaDB more or less. But I presume that those people who implemented PG vector support for n benchmarks, they are experts in Postgres tuning and they specified best parameters Postgres could get in n benchmarks. Those people who submitted a pull request to n benchmarks adding Quadrant support, they tuned Quadrant so that it would perform in n benchmarks. And all those corresponding developers of every database who added support for their database to n benchmarks, I presume they have tuned the configuration files. So I'm just reusing the results, and I try. If Postgres developers did bad job of tuning Postgres for n benchmarks, well, I trust they didn't. Yes, please.
So what was M and what was EF on these charts?
This chart they tried M from 10 to 40. For MariaDB, M was changing from 4 to 48.
M
And
is a default, right?
Now, so n benchmarks, you specify different values. I said and try m equals 4, 6, 8, 12, 16, 32, 48. And try EF, like, 10, 20, 40, 10, 20, 30, 40, and 800. And then it had a lot of different dots here, and then it says, like, so for this one, I get the best results if I use, for example, m equals 20 and EF equals 10, for example. And for this one, it shows best results here. I'll just
You're increasing M and you're increasing EF, and that's the cards as
yes. So n benchmarks was showing the line. If I would connect this dot, this dot, this dot, this dot, this dot, and then all those dots. This is the line that n benchmark shows the best results for every possible. So if you want to have recall of 0.7, that you can get the best QPS if you will use m equals 8 and EF equals 10. And this is the dot you'll have in the graph. It will not show you this dot because you'll get the same recall but worse QPS. It shows the best for every possible dot. That's the line you get in the results. So yeah, this is comparison on the difficult data set.
So Sergei, I think my question would be, you said, hey, if I have an application, right, and I'm a user, right, I know what it wouldn't work if I don't get recall less than 95%, really too much noise. Is there any way I can sort of specify that and MariaDB will figure out what amps inside it?
No, it's very different. It's very different for different data sets. So I was thinking we can do a tool that helps to tune your vector search. But what tool would effectively do? It would still, you need to know your acceptable insert speed. You cannot go slower than 1,000 seconds per million rows. Then you can do m equals 10 maybe.
Well, but I scale my insert speed to get in my hardware.
Mm-hmm.
Right? I can scale my insert to get in my hardware, but I cannot give bullshit results to my users. Right? Which is kind of if my call rate gets too high, right? So
if you want to have, so for this is GIST data set with million rows and 160 dimensions. If you want 95% here, your best option would be m equals 12, but then you'll get rather slow inserts.
You can't really speed up the inserts with better hardware. You're bottlenecked by the algorithm, not necessarily the
speed. Maybe the line for m10 would go somewhere here, and then you can do m equals 10, EF equals 20, perhaps. So I think we could have a tool, I have it written as an idea in Java. It's not just they will try different various calculatory calls with different parameters and provide you with the best set of parameters. But this is basically how it will work. Right. So
insertion takes a long time because you have a lot to write. It's not really hard.
So, as a summary, what we now have in MariaDB, so there's a data type called vector. It supports both text and binary input. There's a vector index type using MHNSW algorithm. Supports different distance functions, Euclidean and cosine, and two tuning parameters, which is M and EF search, providing you those 2 degrees of freedom to tune. If you know PG Vector has EF construction, which I have hard-coded because it would also work. It would allow you to improve insert quality and decrease insert speed. That is, it would work against the same 2 dimensions, so it would be redundant. That's why we don't have it. And I would say yes, it provides reasonably compatible performance. Well, much better than other databases I've on the charts.
So, Sergei, and maybe kind of to follow up an incentive question, right? So, for inserts, right, what is the concurrency on this one? So, if I have 50 threads.
I do not.
So it's a multi-core system. Am I going to get any speed up, or it's like an algorithm is kind of heavy contention and it's kind of serialized?
The other, this is not I don't know at the moment. This is a graph, and if you use MariaDB, then it's a table of no concurrency. If you use MariaDB, then every insert it modifies nodes along the path, and MariaDB is taking rollouts on them. So if you start inserting in parallel multiple rows into an empty graph, then they'll get immediately. Everybody will be waiting on the rollout on the root node, and you'll get no concurrency. After I would think the best performance you'll get is insert rows in small batches, committing after each batch. Then nodes that go into different parts of the graph, they will not be conflicting and they could be inserted in parallel. But I need to tune and find the best insert pattern that gives you the most concurrency. I did not do that yet.
Yeah, okay, but because especially for inserts, right? Typically,
that's fine. That's for
level,
inserts.
right?
Yes.
So my question is,
yes.
How can I parallelize that?
Yes. So I just need to. I have some ideas of what the best load would be to give the most performance, but you need to touch different parts of the graph. I need to experiment with that. I did not do that. Two features I want to highlight specifically. So this is a very normal and expected, and that's how everybody believes it should always be. A scale semantics. If you have a select, you have where, you have a limit, then you get. If you have limit 5, you get first 5 rows that match the where clause. This is how things should be. This is how the world works, but not in the world of those algorithms of vector search, because all those vector search algorithms, they call k nearest neighbor because they retrieve. If you ask it to retrieve 10 nearest vectors, it will find you 10 nearest vectors, and then you apply the vector search and you get less rows than you wanted. That is, in vector search algorithms, in vector search databases, where is naturally applied after the limit, which is not what we want, and it takes some reworking of the algorithm to have a normal SQL semantics of limit of where, and very few vector databases do that. Postgres does it since gvector has it in last October or November, I think. And yes, the second point, that MariaDB stores vectors using 16-bit precision per coordinate, which is half the size of 32-bit floats, so the indexes are half the size of the data. But it's important to distinguish that there are a few databases that use half-width floats, which this is not. If half-width floats have 8 to 10 bits precision, and we have 16-bit precision, so we lose a lot less precision per coordinate, meaning the results are much more exact. We gain a lot of speed by doing that, and we lose almost no precision compared to other implementations that use floats, where they do get speed, but they lose a lot more precision because they have by losing precision, I mean they have worse recall. And we get pretty much the same recall, but more speed and half the specs. To my knowledge, nobody is doing that. It's at the moment MariaDB is supported by Llama Index, thanks to SkyScale people. It's supported by Spring AI. It'll be in Hibernate 7. The pull request already accepted, and there are pull requests for LangChain.js and LangChain4j, and there's discussion to get implementation into LangChain Python, but LangChain community turned out to be much slower than Hibernate or Spring AI communities. So these pull requests are not closed yet. So it will be, I believe, LangChain and Python.js and Java, but at the moment they're still applied in that time. Limitations, well, of course there are some limitations. At the moment you can only have one vector index per table, and it cannot store null values. It only works for in a DB MySQL area and does not work for partition tables. And it's safe is not supported. Yeah. And future plans, perhaps adding more distances after, well, we'll see convincing use cases for using them, or more vector search algorithms. If flat is something that PG vector has, it provides, it's much faster, but as I said, it's trade-off, so recall is much worse. And this n comes from, so there are two, the vector search problem is, there are two different vector search problems. Basically, there's split by scale. There's this vector search problem called like million scale, and there's billion size scale. Billion size scale is you have like millions or tens of millions, maybe hundreds of millions of vectors. That's where the whole data set fits in memory. This is what MariaDB and most of the other vector databases do. And billion scale means when vectors definitely do not fit in memory, and this is the algorithm for this kind of size. We do not implement an algorithm that works sufficiently good in billion scale, for billion scale size. We need to improve observability, provide some information schema table status variables to observe some information about vector indexes. Maybe we add more performance by adding like quantization and parent tricks. Remove limitations I had on the previous slides, those kind of things. Where it's in MariaDB server 11.7 and naturally 11.8. In MariaDB Enterprise server 11.4, starting from the version 11.4 or 5. Yeah. Thank you.